Let's get going. So today we're going to start to talk about model-free prediction. So what that means is taking something like an environment that could be represented by a Markov decision process, but no one gives us the MDP, and we still want to solve it. And so I think up to this point you should be wondering, correctly, well, this is all very well, but what if I don't know the exact equations governing the way in which my factory operates? What if no one tells me, how the pollution level which comes out of the smokestack really depends on the torque which I put into the engine and so forth? What do you do in those situations? And the answer will be we'll start to understand that in this class, where we'll talk about model-free prediction. So methods for which no one tells us the environment, and the agent still has to try and figure out the optimal way to behave. So we're just going to start by introducing the basic ideas. And then there's going to be two major classes to model-free prediction that we're going to talk about. First of all, Monte Carlo learning, which in a nutshell we use to mean methods which go all the way to the end of a trajectory and estimate the value by just looking at sample returns. And then we'll talk about another family of methods which also is model-free and can be significantly more efficient in practice, which are temporal difference learning methods. And these are methods which just look one step ahead and then estimate the return after one step. And then what we'll see towards the end of the class is that we can actually unify these approaches, and there's a whole spectrum of methods known as TD lambda, where we can unify and kind of go any number of steps along the trajectory to come up with a viable estimate of what the value function is for our problem. So that's the goal. I anticipate that we will probably get to here, but there's some details which are sort of deferred to an appendix again, which basically give the sort of formal proofs of the equivalence between Monte Carlo learning and TD learning. So that might be left until after this lecture. You can look at it in your own time. Okay, so let's start with the introduction. So let's kind of just take stock of where we're up to so far. So last lecture, we saw in the previous lectures what the definition of a reinforcement learning problem is, and we formalized these environments, a large class of environments, by using a Markov decision process. And in last lecture we saw how to solve a Markov decision process, and by solve we meant find the optimal behavior in that MDP that maximizes the amount of reward that the agent can expect to get from any state in that environment, any state in that MDP. But this was all for a known MDP, so someone had to plug in the dynamics of that MDP and the reward function for that MDP, and then you could use dynamic programming to turn the handle, apply these iterative equations using the Bellman equations, back up those Bellman equations again and again and again, and we could solve it. We could output the optimal value function and hence the optimal policy for that MDP. And what we did last lecture was we broke it down into two pieces. We started off by first of all using dynamic programming to evaluate a policy, and then in the second part of the lecture we saw how to use that as an inner loop, so once we knew how to evaluate a policy we could find the optimal policy. And what we're going to do with model-free methods is we're going to do something similar. We're going to give up on this major assumption, which is that someone tells us how the environment works, which is really unrealistic for most interesting problems. And what we're going to talk about instead is these model-free methods, which go directly from the experience, the interactions of the agent with its environment, directly from those interactions to a value function, and hence a policy. But what we're going to do is, just like in the dynamic programming case, we're going to break it down into two pieces. We're going to break it down into policy evaluation, and then we're going to use our methods for policy evaluation to help us do control. And so what we're going to do is this lecture we're going to focus just on the policy evaluation case. We're just going to look at prediction. We're just going to ask the question, if someone gives us a policy, how much reward will we get for that policy? And we're going to try and figure out how we can do that entirely model-free without anyone telling us the dynamics or the reward function of the environment. So now you can just run your factory and see how much reward you get and estimate the value function directly from just trying things and seeing what happens. And next lecture we'll use these core ideas to actually do control and find the optimal value function and hence the optimal policy for the MDP. Okay? So there's two distinctions we're talking about here. Distinction between planning, which we did in the last lecture with a known model, and this and next lecture we're doing model-free, full reinforcement learning problem, model-free, no one tells us the environment. And the second distinction is between prediction and control, whether we're just evaluating a given policy or whether we're trying to optimize for the best policy. And that's this lecture and the next lecture. Okay? So this lecture, model-free prediction. how to figure out the value function for an unknown MDP when someone gives us the policy. Okay, so now let's talk about our major methods for doing this. You should be thinking, well, how can I do this? How can I figure out the value function when no one even tells me how the world works? But we'll see it's actually straightforward. And our first method is Monte Carlo learning. It's not necessarily the most efficient method, but it's extremely effective and actually very widely used in practice. And the idea is just to learn directly from episodes of experience. So we don't need knowledge of the MDP transitions and rewards, so this is model free. And what we're going to do is look at complete episodes. So this is really suitable for episodic tasks where you start, it's like a game or something. You start at the beginning of your game and you play for some number of steps, and then the episode always finishes, always terminates. And what we're going to do is we're going to go all the way through our episodes, and we're going to use the simplest possible idea to estimate the value function, which is just to take sample returns. So we're going to look at, one episode I got a return of 5, the next episode I got a return of 7, so we can already estimate the value function from our start state as being 6, the average of 5 and 7. So we're going to use the simplest possible idea, which is just to look at sample returns and average over them. And that's Monte Carlo reinforcement learning. Now there's a major caveat here, which is that this only works for episodic MDPs. You have to terminate to be able to form this mean. And we'll see some other issues with Monte Carlo learning, but nevertheless it's such a core idea. I think we should begin there. It helps us to understand the key intuitions, and once you can do Monte Carlo learning, you can build up a value function, you can solve for that value function, you can do all of reinforcement learning with this very simple idea. So let's see how this actually works a little bit more by going in slightly more into detail. So what's our goal first of all? So we're going to try and learn this value function, the expected future return from any state. Well, what we're going to do is just observe some episodes of experience under the policy that we're interested in evaluating. So if we want to know what happens following the random policy, just going to have our robot, it's going to wander around randomly for a while. That's one episode. We're going to do another episode. I'm going to wander over here. And then we're going to look at those episodes of experience. We're going to look at the stream of states, actions, rewards that we sampled from our policy and from the environment. And what we're going to look at is the total discounted reward that we got from each time step onwards. Okay, so that's this GT, that was the return. The return was just the reward from that time step onwards until the end of the episode with some discount factor. So this is going to be different for every time step in the episode. Like, the return that I see from the beginning of the episode includes everything all the way along this trajectory, whereas the return from halfway through only includes the rewards from halfway until the end. Okay, and what we're going to do now is we're going to estimate the value function by basically just taking this expectation here. So the value function is the expected return from time t onwards if we were to kind of set our state to that particular point. So if I was to set my state to here and look at the expected return from this point onwards, that's the definition of the value function. So all we do in Monte Carlo policy evaluation, this simplest idea of Monte Carlo learning, is we use the empirical mean return in place of this expected return. So we're just going to replace this expectation with an empirical mean, and we're going to collect as many samples as we can from each of these states of what happens from that point onwards. And then the only issue is how do we do this when we kind of don't get to reset our state back to that exact point repeatedly, and we want to kind of figure this out for all states in our environment. How do we get the mean for all states just from trajectories? And there are two different ways we can do this. And they both work and they're both effective, but there's a sort of subtle difference between them. So the first approach is what's called first visit Monte Carlo policy evaluation. So to understand this, imagine that you've got some loop in your MDP where you come back to the same state repeatedly. But to evaluate a state, what we're going to consider is the very first time we visit that state. We're going to basically say, the first time I get to this state here, in some trajectory, even if I come back to that state later and then go off and get some reward afterwards, we're just going to look at the first time I arrived at that state. And when I reach that state for the first time, I'm going to increment a counter to say how many times I visited that state. And I'm going to add up the total return. And now I could just get the mean return from that state onwards. So we consider, in each episode, we're going to look at the first time I visited that state. We're going to measure the total return we got from that. And we're going to take the mean over those total returns from that point onwards. And all we're going to use is a very simple mathematical result, which is the law of large numbers, which basically says that when you take a mean of a bunch of ID random variables, that the mean of those random variables actually does approach the true expectation. So that tells us that if we see enough episodes, if we just randomly sample enough episodes, this very simple idea of Monte Carlo learning really will converge on the true value function for our policy as we get more and more samples. And the only requirement is that we somehow visit all of these states. And we do that by just sampling along our policy itself. So we generate trajectories along our policy, we do that again and again and again, and we just look at the returns that we get from the first time you visit a state onwards, and we average over those returns. Okay? People understanding? Questions on that? Good. Yeah.
I'm slightly confused because every time we enter the step, we increment the counter, right? Or because if we...
The first time we visit that
so
state.
it will be always one.
No, because the counter persists over multiple episodes. So what we're trying to do is get an average over multiple episodes.
Okay.
So this is counting how many times over a set of episodes, how many times have we visited that particular state for the first time. And this is telling us the total return over many episodes. We're adding on the complete return for each episode here. So this is just a very simple way to say we just take the mean of all of those returns. Okay. Yeah.
If the state space is really large, then the number of episodes you need to run, doesn't that go up exponentially?
No. Well, so first of all, we can ask how quickly does the law of large numbers, basically if you want to know how quickly does it approach the mean, that's the central limit theorem. So we basically know that you normally get some normal distribution, and the rate at which the error reduces roughly sort of with a variance of 1 over n. Okay, so the number of episodes you need to reduce the variance. So the number of visits you need to any individual state is kind of the error you get has a variance which reduces with 1 over n, which is completely independent of the size of the state space. So you just need to see that returns from that state that number of times, and that very quickly will reduce your variance. And the size of the state space, again, the only thing which matters is that we see these states enough times. So each time we're going to see a trajectory, and we basically want to make sure that every state in that trajectory we're maintaining this mean for. So again, as long as your trajectory visits the states that you're interested in, it basically depends on the frequency with which you visit those states. So you have to see those states some number of times, and so it depends on how frequently your policy visits the states that you care about seeing the value function for. But again, that's actually independent of the size of the state space. So that's one of the nice things about these model-free methods, actually, is they don't have, unlike dynamic programming where we're doing full sweeps, we're just sampling here, and sampling actually kind of breaks this dependence on the size of the problem. Okay, so that's first visit Monte Carlo. Let's look at a very subtly different version. Sorry, quick question.
I don't understand how can you make sure that you visit all the states in each of these?
Okay. We'll talk about that more next class, so I'm going to defer that question mostly to next class. For now, we're just doing policy evaluation. So all we care about is how good are the states that we visit under policy pi, and the way that we make sure that we see all the states that we care about under policy pi is by following policy pi. So just by following the policy that I'm trying to evaluate, we guarantee that we see all of the states that are reachable under that policy. And so we will see all of those states. And that idea is sufficient for now to make sure that we see enough visits to all of those states. In subsequent lectures, your question's really actually a very interesting one, which is how do you make sure that you cover the whole state space when you're trying to find the best policy? And that's a whole issue of exploration that comes up in reinforcement learning. It's one of the fundamental questions of reinforcement learning. But here we're just trying to evaluate this policy, so it's enough to just run episodes with that policy. If I want to know what happens if I follow a straight line to the wall, all I need to do is just keep following that policy of running a straight line towards the wall, and I'll see all of the states which are of interest, and I can evaluate those states because I've run that policy already. Okay, second idea, very closely related, is every visit Monte Carlo policy evaluation. So now to evaluate a single state S, if we've got this loop again, the only difference is now that we're going to consider every visit to that state instead of just the first one. So we're basically going to come around, and if I could do my loop, I'm going to come back to it again, and I'm going to include both my original estimate of the return, including the loop, and also my second estimate from that state the second time I visited to it. So basically, in one episode, you can increment the counter multiple times for this state. Each time you visit it, you'll increment the counter, and you'll add on a different value of the return based on the point which you were up to at that time step t for each of those visits. Apart from that, the algorithm's identical. We still can use the law of large numbers. This thing still finds the true value function. Everything's good. So both of these are valid estimators of the mean, of the expectation, by just taking samples of the mean in different ways. Yeah.
Are there any intuitions which one is better, and in which case which one should use?
So it sort of depends on the setting. Actually, when we talk about TD lambda, I'll come back to that question, that there's different types of traces you can use, and they correspond to every visit and first visit traces. And there's some evidence in favour of both, depending on the domain, actually. Okay, so let's make an example. So I just want to talk about this. It's a little bit related to the assignment. So so the idea is we're going to consider, how can I train you up to go and break the casino like after this class? Don't hold me to that. I don't want to be responsible for anyone losing money. Casinos actually don't follow exactly this. Is a simplified version of blackjack, so you won't be able to use this and really win money. But we're going to consider the game of blackjack, sometimes called 21 or pontoon, things like that. And it's a very simple game where the dealer basically you get dealt. You start off with 2 cards, and the idea is to get as close as possible to 21 in the sum of those 2 cards without going over 21. So you just add up the face values of all of your cards, and if you ever get dealt a card such that the sum of your cards goes over 21, you're bust and you lose. But the closer you get to 21, the more likely you are to beat the dealer, who also has 2 cards, and is going to play the game the same way. And if your total beats the dealer, then you win the game and you win some money. Okay, so that's the game of blackjack. And how many people know the game, by the way? Good, yeah. Okay. So the way we're going to represent this, we're going to represent it as an MDP, and we're going to treat the state as having basically 3 different variables in the state space. First variable is the current sum of our cards. So if we've got 3 cards and the sum of those cards is 17, we're going to say we're in a state with a sum of 17. And note that we're not going to consider sums below 11, because for those states we're just going to automatically ask for another card. Because for free you can ask for another card, and it's not an interesting decision at that point. If you have less than 12, there's no interesting decision to make, because you'll always ask for another card. Okay, so we're only going to consider the states where we actually have an interesting decision to make, where the sum of our cards is between 12 and 21. And we're going to look at what the dealer's showing. So when you're playing your game, you see one card of the dealer's, and that you can use that to decide whether you should ask for another card or not. And your goal is to, without having seen the dealer's next card, how can you decide on this decision of whether to ask for another card and possibly go bust, or to stick with what you have. So you've got those 2 actions, to stop, stick, or to twist. And if you do stick, then the dealer plays out the game. You just think of that as the turn of the environment. The dealer plays out the game all the way to the end. That's like 1 step of the environment. And then you get +1 reward if your sum's greater than the dealer's sum, 0 if it matches, and -1 if you've got less. And if you twist, then you get -1 if you go over 21, because you go bust, and 0 otherwise. And for the transition structure of this MDP, the only thing we're going to add to it is this idea that if you've got less than 12, we're going to automatically twist. So we're not going to, that's just part of the MDP then. So you only actually make actions where there's an interesting action to make. And there's this sort of auto twist as part of the environment if you have less than 12. Okay, so let's apply Monte Carlo policy evaluation to this problem. And so next class we'll actually see how to really find the optimal policy. For now we're just doing policy evaluation. And what we're going to do is we're going to choose a really naive policy, and we're going to see what happens with that naive policy. And so the policy is going to be, we're going to stick if the sum of our cards is 20 or 21. And otherwise we're always going to twist. So even if we've got 19 or 18, we're just going to twist. And we want to know, well, how good or bad is this? And we're going to consider, oh sorry, I forgot to mention one more state variable. So we have 3 state variables. The third state variable is whether we have an ace in our hand, which is usable. That means it can either take the value of 1 or 11. And so it's good to have an ace in your hand. And basically, what we see is that this is basically using, I think, every visit Monte Carlo learning. And what was done here was basically to just roll out 10,000 episodes of blackjack. So to literally play out this game with 10,000 hands and then 500,000 hands and apply exactly the procedure we've just seen. So for these 10,000 hands, every time we came across one of those states, every time we had a sum of 13 and we had a usable ace, and the dealer was showing a 5 or whatever, we would find the appropriate point here in the value function space, and we would update that estimate of the value function a little bit towards the mean of. So for each point here, we're keeping a separate estimate of the mean for that state. And so for all of these states, we update the mean from these episodes, and if you run enough episodes, you start to get the shape of the value function. And what you should immediately see here, this is really to give you a flavor of what happens with these algorithms. You see that even after 10,000 episodes, you still have you get a pretty decent estimate of the case where you don't have an ace, but the estimate where you do have an ace is much noisier, and that's because these are rarer. These states are rarer. So 10,000 episodes, you don't actually see enough cases where you've got an ace to really figure out all of these means correctly. So it's still quite noisy, and you need something like 500,000 episodes to really get the correct shape of this value function. And this shape is telling you something quite interesting, which is, as you'd expect, if the dealer's showing something towards an ace, so the better the dealer has, the worse off your value is. Unless he's got an ace, that's even worse there. And this is your sum. So if you've got 20 or 21, you do quite well in this game. But for anything below that, you do really badly because you've got this very naive policy where you're just going to keep twisting and probably go bust. So we see that emerging nicely from the structure of this value function, just by sampling. So no one told us the dynamics of the game. No one told us the probabilities that govern the game of blackjack. No one told us the structure of the pack, the deck of cards. This was just by running episodes, trial and error learning, and figuring out the value function directly from experience. Okay?
Can you just clarify the dealer answers? Does it go ace, 2, 3, 4, all the way up to 10?
Yes. Yeah. Okay.
What about Jack or Queen?
Okay. So Jack, Queen. So picture cards are just treated as tens in this game. So in blackjack, all picture cards have a value of 10. Yeah. Question.
So what this is showing the expected reward given that you're at that state if you follow the policy.
The expected return, which is
Yeah.
the expected return, which is the value function.
Yeah.
So if you were to follow this policy, each point on this diagram, the height of this point on that diagram is showing you your estimated value function, your estimate of how well you will do, of whether you'll win or lose this game. If you're in a situation where you say, where the dealer is showing an ace, and you've got a player sum of, say, 19, this value here tells you how well you think you will do in that game. And so it's the shape of this value function is exactly the information we're after. Like once we have this, we can do all kinds of things. Like the key quantity we're after is this picture. Once you have this picture, you can evaluate your decisions and pick the best decision and make better policies because you can look at the shape of this surface for all different policies and find the best one. Okay. Good. And so the assignment is to work on a similar game, something called Easy 21, which I think you'll have fun just playing around with and trying to understand. And you can run all kinds of reinforcement learning algorithms to figure out not just policy evaluation, but to find the optimal policy for that game.
Does that value function tail off slightly with the 10 compared to the 9 on the bottom right-hand side there?
Yes.
I don't understand why it would do that.
It might just be noise in the evaluation, I would
Well,
guess.
the 10 would be a better estimate, right? Just because you have more tens. If you bundle up together all the jacks and queens and kings, or maybe not better, but different.
But if the dealer's got a 10, it's a better hand for the dealer, right? That's why you get the worst return.
No, because you're on 19. When you're on 19, you don't want to get a 10. That's why it's improving slightly all the way up, because you don't want large cards. So you're happy when the dealer's got large cards.
Well, it's a little bit unclear, right? So it depends on the strategy the dealer's using to twist, actually. Right. So I think it depends. So it might be that the dealer has the same strategy as us, in which case having something like a 7 or 8 is actually a bad situation for the dealer, because they will probably twist and most likely get a 10 again, and then they'll most likely twist again, and and there's a higher probability of going bust here than if they've already got a 10, in which case they're likely to get another 10 because there's more of them, and then they'll stick. So I think it depends on the dealer's strategy.
So to program this, you actually have to program the dealer strategy as well, which we don't know.
You do know for the assignment. Okay. So let's move on. But I think that illustrates that the value function depends on all kinds of factors. Like the actual value function does depend on every aspect of the environment. It depends on how the dealer acts. It depends on the deck of the card, the randomness, how many 10s there are compared to 9s and 8s. All these things affects the value function, and yet we don't need to tell our agent any of those things. Just by sampling the returns, we're able to go directly to the right thing, which is the value function, and hence the optimal behavior in the next lecture, without needing to explain anything about the dynamics. And that's the power of model-free reinforcement learning, that you can go directly to the result without going through these intermediate steps. Okay, so far we've talked about this sort of explicit computation of the mean. So what we're going to see is that this can be done incrementally. We're going to start to move towards online algorithms, which step-by-step update the mean. So this slide is it's probably a well-known result. Sorry if you guys are aware of this, but it's just to show that the mean can be computed incrementally. You don't have to, first of all, make the sum of everything and then divide the sum by your count. You can do it incrementally. And so very briefly, if the mean of k elements is just 1 over k of the sum of those elements, what we can do is we can split this sum out into a sum up to k minus 1, so the previous k minus 1 elements plus the kth element. And then what we can do is just observe that this sum here is k minus 1 times the mean up to k minus 1. So this sum here is just, you can take your previous mean, multiply it by k minus 1, and then add on your new element, and divide by k again. That gives you your new mean. And then if we just rearrange these terms, we see that if we collect together our xk's, then we've got 1 over k of them here, and our mu k's we can basically pull out here, and we can subtract off the 1 over k mu k that we have here, and this is the k times 1 over k of mu k that we pull out here. And what we see is that you can basically, the new mean is the old mean plus some step size, 1 over k, a little increment towards the difference between your new element and what you thought the mean was. So we're going to see a lot of algorithms which take this form. There's an error term here. So think of this error term as this being your estimate of what the value is going to be. Before you actually see this new element, you've got some estimate of what you think that value is going to be, which is your previous mean. So you think that your elements are going to have this value on average. Then you see your new element here, and there's some kind of error between what you thought was going to happen and what actually happened. So that's your error term here. And now what we basically do is we update our mean a little bit in the direction of that error. We're going to see a lot of algorithms which take that form, where you sort of correct, you have like a prediction, and you correct that prediction in the direction of the error. So basically, if you were estimating your mean too low, and you see something higher, then you need to increase the value of your mean in the direction of the error between what you thought the mean was and what you actually observed. So that's the idea of these incremental mean computations. And we'll pretty much see that every algorithm in the remainder of this lecture takes this form. And so let's first of all do this with incremental Monte Carlo updates. So we're going to take our Monte Carlo algorithm and we're just going to make it an incremental update. So we're going to do it episode by episode now, without keeping track of these sums and these visit counts. You still need the visit count, but without keeping track of the sum. What we're going to do is we're going to take the same algorithm, so for each state with some return that we've seen. So for now, we'll just keep the visit count. And what we'll do is we'll update every time we see that state. We're going to measure the return from that state onwards. And we're going to look at the error between the value function, that's what we thought the return was going to be, and the return we actually observed. We're going to generate some error. We're going to update our mean estimate for that state a little bit in the direction of that return. Okay? And so this is exactly the same. We've just transformed our computation of the mean in this way. Yeah, question?
In example, you put the return in the end, we didn't have the intermediate return. And here you have intermediate return.
No, no. So we're not computing intermediate returns. That's the next part of the class, actually. So I'm glad you said that. So what we're doing is we're still getting the complete return, but it's only incremental in the sense that every episode we're going to update our mean, and just it's a trivial rewrite of how we compute the mean. And the reason we're doing it this way is we're showing how this is going to develop towards other algorithms. So we're going to replace this 1 over n by other quantities, and we're going to replace the target we move by other quantities. But it's just to show that, so we're doing exactly the same computation as before. Nothing has changed. It's just an incremental mean update, just to put things in the form that we're going to use later. So we're doing things episode by episode. We're incrementally updating our estimate of the mean for that. Yeah.
But we add these values after we finish the episode, right? Because then we know the whole value function for this step.
Yes. So this is all forward-looking. Everything with Monte Carlo so far, you have to wait until the end of the episode to see the return that you got, and then you have to go back to the state that you want to update and say, okay, well, from that state, I ended up getting 100 points of reward, and now you update your estimate from at the end of the episode. So this is one disadvantage of Monte Carlo that we'll address shortly. Okay. So really what we're going to move towards then is we want to move towards algorithms that don't have to maintain these statistics and just incrementally update themselves. And one way in which this can be done is actually by forgetting old episodes. So you don't necessarily want to take a complete mean. Sometimes you actually want to forget the stuff that came a long time ago. And one way you can do that is just by having a constant step size here. And this gives you like an exponential forgetting rate when you're computing your mean. It gives you an exponential moving average of all of the returns you've seen so far. So it's another way to compute a different type of mean now, where we've replaced our 1 over n by this fixed step size alpha. But the concept is still the same, that we had some estimate of what we thought the mean value was going to be. Then we saw some return from that state onwards. That gives us an error term. And now we just move our value function a little bit in the direction of that error. So now we don't move all the way to correct this exactly to the overall mean. We maybe under or overcorrect, depending on what the value of alpha is.
But the only thing which we got here is like we don't have to store one integer, right? Which is n. So this is not a huge advantage.
So the question was, is there an advantage to this beyond not having to store n? So maybe I wasn't clear. So first advantage of this approach is that this applies to non-stationary setups where things can be drifting around. So in the real world, stuff is changing. You don't want to remember everything all the way into the past, because stuff that came 100 years ago you kind of want to forget about, and including that in your mean is just going to slow you down and sort of give you baggage that you actually want to let go of. And we'll actually see as the lectures develop that we're always in that case in reinforcement learning. We're always in the case where things are non-stationary, because although in this lecture we're evaluating a fixed policy, in general we'll start to improve the policy, and so the thing which we're evaluating is getting better and better and better. And so that's why we prefer these non-stationary estimators rather than taking the true mean. In addition, it's something where we can have memoryless algorithms where a new step comes in, and we just look at that step and we can do an update without having to track these statistics about what's come before. I think that's a less important detail. So we're just in this setup where we're looking at algorithms where we move a little bit towards the sample that we've seen. Okay, so that's Monte Carlo learning. So very simple idea. You run out episodes, you look at those complete returns that you've seen, and you update your estimate of the mean value towards your sample return for each state that you visit. Okay, now we're going to move on to a different class of methods which really do now break up the episode and use incomplete returns. So let's think about this. What do we mean by temporal difference learning? So again, like Monte Carlo learning, these methods, TD methods we call them, they learn directly from actual experience, from interaction with the environment. It says episodes here. Actually, TD applies to the non-episodic case as well, continuing case. TD again is model free. So again, we don't need to know how the environment works, the transition structure, the reward structure. Again, we don't need to know how the dealer works or the deck of the cards, or any of those details. But one difference from Monte Carlo is that now we're going to learn from incomplete episodes. So we don't have to go all the way until I hit the wall and see how much reward I got from that complete trajectory. I can basically take a partial trajectory and now use an estimate of how much reward I think I'll get from here up until the wall in place of the actual return. So this idea is called bootstrapping, this idea of substituting the remainder of the trajectory with our estimate of what will happen from that point onwards. That's called bootstrapping, where we basically update our guess of the value function. So I'm going to start off guessing how long it's going to take me to get to the wall. I'm going to walk some number of steps. I'm going to make another guess of how long it's going to take me to get to the wall. And I'm going to update my original guess towards my subsequent guess. That idea is called bootstrapping, and that's the fundamental idea behind TD learning. Okay, so let's make that more concrete. So again, the goal is the same as we had before. We're trying to learn our value function, v pi. We're just doing policy evaluation in this class. The next class we'll turn this into a control method. And we're just going to look at our interactions under some policy. So if I follow my random walk around, how well will I do? How much reward will I get? And I want to estimate this efficiently. And now we're going to try and do this online. We're going to try and just look every step. I'm going to make a new estimate, adjust my estimate of the value function without waiting until the end. So let's think about what we've done so far. So in Monte Carlo, what did we do? Well, we were in some state. We had an estimate of the value function. This was our previous estimate of the value function. We got our return. We looked at the error term between our estimated value and the return, and we updated our value function a little bit in the direction of that error. So what we're going to do now is we're going to use temporal difference learning, and let's consider the simplest version, TD0, and we'll understand later what that 0 means. But what this means is now we're going to update our value function towards the estimated return after one step, and I'm going to estimate how much the return is going to be. And our estimate basically consists of two parts, just like in the Bellman equation. So the estimate consists of two parts, which are the immediate reward. So I think the total reward is going to be the immediate reward plus the discounted value of the next step. So it's just like the Bellman equations we saw in the previous lectures. And now what we're going to do is we're going to substitute this estimated return, and we're going to use that instead of the real return. So we're basically going to take exactly the same algorithm we had before. We're going to pull out the real return, and we're going to replace it with an estimate of the return, which consists of these two pieces, the immediate reward plus our estimated reward over the rest of the trajectory. So we're coming up with an estimated biased algorithm, and we'll see the consequences of that bias shortly. Okay. So this term here, this red term here, is what we call the TD target. This is the thing which we're now moving towards. It's like a random target. It depends on exactly what happens over this next time step. But we get some immediate reward and some value at wherever we happen to end up, and we're going to move towards that thing, and that thing's called the TD target. And this whole error term here, the difference between what we thought we had and the difference between our TD target and our estimated value before we saw this step, is called the TD error. The difference between our estimate before and our estimate after taking a step. That's the TD error. So why is this a good idea? I mean, I think the simplest example would be, imagine you're driving along, you're driving in your car, and if you're doing Monte Carlo learning, you have to basically, when would you update your value function? Well, imagine that you drive along and consider the following scenario where you're driving, you see suddenly a car that comes hurtling towards you, and you think you're going to crash, but then you don't actually crash. At the last second, the car swerves out of the way, and you don't actually crash. So in Monte Carlo, you wouldn't get this negative reward. You wouldn't have a crash. You wouldn't be able to update your value to say that you almost died. But in TD learning, you're in this situation where you think everything's fine. Then you drive along, and you're now in a situation where you think you're going to die. You think this car crash is going to happen. And so you can immediately update the value you had before to say, oh, that was actually worse than I thought. Maybe I should have slowed down the car and anticipated this potential near-death experience. And you can do that immediately. You don't need to wait until you die to update your value function. So there's a great slide by someone I know in reinforcement learning. He puts up these backup diagrams that we saw in the last class, and with this big skull and crossbones saying, you can't back up death. Anyway. So let's do another driving example. So this example is from Sutton and Bartow, so you can look at this in your own time. But the idea is basically that, I'm driving along, I'm on my way to work. Let's imagine I didn't actually do my usual horrible commute on the train and was actually in a car. I start off by making some prediction of how long it's going to take me. And so these rows basically show how much time has passed so far, how much time I think it's going to take from this point onwards, and the total of these two columns here, time so far plus predicted time to go. Okay, and I start off thinking it's going to take me half an hour to get to work. But maybe then I leave the office and I reach the car and I see that it's raining, and I'm like, oh, I'll have to drive a bit slower, I'll probably be more traffic. It took me 5 minutes, and now, okay, maybe I hadn't really adjusted I now think it's raining, so it's going to take me slightly longer. So I think it's going to take 35 minutes to get to the office now, giving a total of 40. Next step, I get off the motorway, highway, and that's taking me 20 minutes. And now I think, okay, that went a bit smoother than I expected, so now I think there's only 15 minutes to go, giving a total of 35. Then I get stuck behind a truck and think, oh, actually it's going to take me a bit longer than I thought, so now I kind of increase this. Think, oh, there's actually 10 minutes to go now, it's going to take me 40 minutes. And then I get on the home street, and I've only got, things are going okay, but it took a little longer than I thought. I think there's still 3 minutes to go, and then eventually I get there, and it actually took, in total, 43 minutes. I realise there's no more time to go, and so the total, everything lines up at the end, and we think that there's nothing left, and it took us 43 minutes in total. So now how would we actually update our value function based on this trajectory of experience? So these figures really show the difference between Monte Carlo and TD in practice. And in Monte Carlo learning, if we look at each point along that trajectory, this shows basically how much, like the total predicted journey time, so basically what we thought, so it actually took 43 minutes along here, but at every moment I had some prediction of what that total time would be. So here I thought it was going to take 30 minutes, it actually took 43. Then it sort of, I reached the car, and at that point I thought, uh-oh, it's going to take 40 minutes, and then things were going better, so I thought it's going to take 35 minutes, and so forth. And at each step along this, using Monte Carlo learning, you update towards the actual outcome. You have to wait until you finally get there, see that it actually took 43 minutes, and then update each of your value estimates along the way towards that 43 minutes. Okay? Whereas with TD learning, it's quite different. At every step, it's like you started off thinking it was going to take you 30 minutes. After one step, you thought it was going to take you 40 minutes. So you can immediately update there already. You don't need to wait until anything else happens. You can say, oh, I was in a situation where I thought it was going to take 30 minutes, but then I saw it was raining, so probably my 30-minute estimate was too optimistic. Let's adjust that a little bit towards 40 minutes. At the next step, I started off thinking it was 40 minutes, but then things went quite smoothly on the highway, so I can immediately pull this guy down and say, well, maybe I was a bit pessimistic and I should move this towards this guy. And then, you have to realize that you might get stuck behind a truck, so that might pull you back up again, and so you should move this towards your subsequent estimate. And eventually you get grounded by the actual outcome. So you're always updating guess towards a guess, but eventually you get grounded by this actual outcome where you really get there, and that's the end of your episode, and you get your real reward of having a day at work.
Can I just check, in this example, what is the goal and what are the actions?
So first of all, okay, the goal is so the reward function is the time that it takes you. So think of that as the reward function. So the reward function is time. So you could think of this as the goal is to get to work, and you get -1 per step. So if you made all of these negative, you could think of that as a goal, and that would be a well-formulated Markov decision process such that the optimum corresponds to getting to work as quickly as possible. The actions there are no actions here. Think of this as a Markov reward process. We're just trying to do policy estimation. The policy could be anything we want. The policy is just driving your car, and the action space it could be anything. And the reason it doesn't matter is we're just trying to evaluate whatever that policy is and whatever that action space is. For now, we're just looking at how to evaluate how much reward I got from this particular trajectory. Remember, you can flatten any MDP into a Markov reward process given a fixed policy. That's kind of what we're doing. We're just evaluating this thing. We're just trying to understand how much reward you get, independent of the action space. Next class, it will matter much more what the action space is, because we're going to pick actions so as to optimize our decisions. Okay. So is this a good or a bad idea? So, well, there's several ways in which it's a good idea. So the one we've just seen really and focused on is that TD can learn before you see this final outcome. So you don't need to wait until you crash and die. You can already start learning after just one step. Whereas Monte Carlo has to wait always until the end of the episode before you actually see the return, and then it backs it up retrospectively. And one advantage of this is that TD can learn in situations where you never see the final outcome. So this basically means, what if you get incomplete sequences? What if you're learning from in some situation where you just don't get to observe the return at the end of the episode? We'll see this later when we do off-policy learning. This really happens a lot in many cases. Or what happens if you want to deal with continuing environments that just go on and on forever and you never get to the end? Well, Monte Carlo just doesn't apply there. I mean, you can go to some arbitrary horizon in the future and just back up from there, but there's always some error introduced. Whereas TD really works. It really works in all of these cases. Even if the environment just goes on and on and on, you just update now from what happens at the next step, and if your steps go on forever, that's okay. Everything still works. You'll find the true value function regardless. Okay?
Does it learn the same behavior? So if you have a car, and the car almost crashes, but it doesn't. And the reason that it doesn't is because other people avoid a lunatic. So when you're learning step by step, you're going to learn a behavior that you're scared of crashing. But if you only learn from the very end, you would never learn something which encouraged you to avoid your own manic behavior, because by the time you get to the end, you don't suffer the consequence.
So it learns. We'll answer that question properly. It does. So the answer to that question is a really good question. Does TD find the same answer as Monte Carlo? We're going to start to address that. The basic answer is that TD finds the true value function. It finds the true value function. As long as you run this thing out, it will always ground itself, because even though you correct yourself based on your guess, and that guess might not be right, that guess will then be updated towards something that happens subsequently, which will ground it more and more. So all of your guesses are progressively becoming better, and that information backs up such that you get the correct value function. So it's fine. Okay. So we're trying to understand the pros and cons of TD compared to Monte Carlo. So one other issue which comes up, which is a major difference between the algorithms, is this bias-variance trade-off. So the return, this sample that we get of all the rewards in the episode, we can think of in Monte Carlo, this return that we used. So in Monte Carlo, we just used this whole sequence of rewards that we actually sampled from our MDP, and that's an unbiased estimate of the value function. So the value function is just, the definition of value is the expected return. So that's what we mean by unbiased, that this is just a sample of this expectation. So if we actually update towards the return, we're not introducing any bias. The law of large numbers will take effect. We'll really find the true value function. Everything is good. What if we were to use the true TD target? By true TD target, we mean that we drop in the true value function. Like if some oracle told us the true value function, and we used the immediate reward plus the true value at the next step, that would also be an unbiased estimate of the value function. And we know that from the Bellman equation. And the Bellman equation tells us that the value function is equal to the expected reward plus discounted value at the next step. That was the Bellman equation, the Bellman expectation equation from lecture 2. Okay, so either of these cases gives us an unbiased estimate. But what we actually do in TD is we don't use the true value. We don't have an oracle to tell us the true value. So what we substitute in is our best guess so far of what that value function is at the next step. So the target which we move towards, the target which we're updating our value towards, like I think I'm in some value, and I update towards the immediate reward that I got over that step, plus the discounted estimated value at the next step according to my current estimate. So now we've introduced bias. Like this estimate could be anything. Like I could be wildly wrong. I could initialize with some crazy value for this thing. So we introduce bias into our estimate, into our target, but we reduce the variance. So the TD target is biased, but it's much lower variance than the return. So intuitively, why is it lower variance? Well, let's look at the return. The return depends on, this random variable here, depends on the immediate reward after one step, and then whatever the environment does, it will take us to some next state. That's noise in that transition. There's noise in the reward we'll see here. There's noise in the next transition. There's noise in the reward we get here. There's noise in all of that whole trajectory of of many, many random variables depending on the environment and the agent's policy over many, many steps. There's a lot of noise. It multiplies out over the course of the trajectory. Whereas the TD target, we only incur noise from one step. There's one step of noise in the reward we see. The environment gets to take one turn. We get one random transition, and then we invoke our value function at that next step. So this thing is much lower variance than this thing. We're only looking at the noise over the first step rather than over the entire trajectory.
Your
So-
estimation of the V, st plus 1, is a very noisy estimation.
It's not noisy, it's biased. So it's biased. You have some estimator of V, which may be wrong. It may not have the true value, but it's not noisy. This is at any given time. This is just some fixed function that you're looking up the value. So it doesn't depend on. So the state that you see is noisy, but the value function that the bias comes from the fact that your value function. The bias comes from the fact that this is not equal to this. Okay, so Monte Carlo is high variance but no bias. So some good things about Monte Carlo is as a result of being zero bias, it has very good convergence properties. We'll see later, even when you use function approximation, Monte Carlo just works. It works out of the box. Everything, all the algorithms just converge to the correct answer. It's not very sensitive to the initial value because we're not bootstrapping from the initial value. It will just it still matters where you start. It will take longer to adjust a really wildly wrong value towards the correct value. But it doesn't kind of cycle off itself. It doesn't feed off itself. It's very simple to understand and use. So TD, on the other hand, is much lower variance, but it has some bias. And so you should be wondering, well, does the algorithm even work if it's biased? And the answer, luckily, is yes. And it's usually much more efficient than Monte Carlo because it's so much lower variance. In most situations, TD, we'll see examples of this, TD is generally a much more efficient algorithm. And for the special case we're looking at, policy evaluation using table lookup, it converges to the true value function. So this is true. I'm not going to prove it, but this was proved actually by Peter Dayan, was one of the first people to prove this for the general case. But not always with function approximation. So there are cases, which we'll see, there are special cases where the bias in TD leads to the algorithm not behaving in the way that we would like. But these are quite specific cases that we'll start to address in the next couple of lectures. And it's more sensitive to the initial value because it is feeding off itself in this way. Okay? Yeah, question?
What do you mean? Which function you mean by this function approximation?
Okay, so in a couple of lectures' time, what we'll see is that everything we've done so far is not practical because we're estimating the value function V of S for all states separately. And in most interesting problems, you've got more states than you can count. And so what we'll do is we'll use a function approximator to estimate the value function later. And the question is, do these methods still work effectively? And the answer is yes, except for certain specific cases that we'll deal with. Okay, let's make this a bit more concrete with an example. So this problem here is a random walk. So what's happening in this problem? It's like one of the simplest MDPs you could imagine. In fact, it's just there are two actions, left and right. We're going to consider a uniform random policy that goes left 0.5, right 0.5. If you end up in this state here, the episode terminates and you get net zero reward. These are the rewards you get for the transition, so zero reward, unless you make it all the way to the right, in which case you'll get a reward of 1. So you're just going to do some random walk along here. If you end up here, that's good, episode finishes with a reward of 1. If you end up over here, that's bad, you get 0. Okay, and then the question is, well, what's the value function for this thing? What's the value of being in each of these states? And we could just use this to get an intuition of, the simplest possible case to get an intuition of how Monte Carlo and TD compare to each other. So if you actually look at the value function and apply TD, so this is applying the TD0 algorithm, what you see is that you can start off with some completely arbitrary value estimate. So let's start off initializing everything to, say, 0.5. And then if you run this for 1 episode, 10 episodes in blue, 100 episodes here in black, we see that this thing starts to flatten out onto what actually is the true value function, which is this straight line up here. Okay, so roughly 100 random episodes here, and you pretty much got the value function using TD0. So how does that compare? So intuitively, that's basically saying that, you know, state A, the value kind of increases as you move towards the 1. So you basically, I think the true value function is something like 1/6, 2/6, 3/6, 4/6, 5/6 as you move along. That's the true value function, which you can find by dynamic programming. Okay, so now what happens if we compare Monte Carlo with TD? You know, is it really true that TD is more efficient? So here we're just looking at the number of episodes that so this is like picking out at each of those stages, like 1, 10, 50, 100. And now we're plotting these learning curves showing how the error reduces in the value function. So what we're looking at on this y-axis is basically the mean squared error, the root mean squared error, averaged over all states. In other words, we're looking at the total error between the true value function and the value function that we've estimated after some number of steps. We're looking at the sum squared error and then take the square root of all of that. Okay, and then what we see is that if we look at in the black lines here, we have Monte Carlo learning with different step sizes. And in grey here, we've got TD learning with different step sizes. And so this is for a small number of episodes. Actually, this same result extends out further. You just have to optimize the step size, and you'll see that, you know, for appropriately chosen step sizes, TD continues to do better than Monte Carlo. So you see this, basically this is showing us the effect of bootstrapping. That by bootstrapping you can learn much more efficiently than incurring the variance of all of this things which come later on in the episode.
Is there any reason that the errors start growing when we increase the number of episodes?
I think it's just the noise in these step sizes are very high. So with these step sizes, you can never get exactly to the true value function. So with a large step size, you basically will oscillate around the true value function within some ball that's governed by the size of your step size. So you don't guarantee to converge all the way to the optimal solution. So if you could, the convergence proofs for TD actually use a decaying step size schedule using like Robbins-Monroe conditions, where you have to kind of do a sort of 1/n some kind of schedule for the step size, and then it really does converge. Same's true for any gradient-based method, you know, Monte Carlo. You would still need to, in many of the cases that we'll see, you still need to decay these step size according to an appropriate schedule. So I don't think it's actually, if you were to plot this out, I don't think it's going up. I just think it stabilizes in that, you know, you're only going to get within whatever accuracy your step size is. If you're jumping around too much with your steps, you can't expect to converge exactly to the right solution. You have to start reducing your steps to get exactly there. Okay. So we've seen so far that these approaches converge. Both for Monte Carlo and TD we converge. We find the true value function as you add in an infinite amount of experience. But what happens if we were to just stop after a finite number of episodes? If we were to just show 3 episodes to our system and then keep iterating on those episodes and learn again and again and again, apply our updates, like repeat those episodes and just keep going over that same data again and again, what would happen if you applied either Monte Carlo or TD? Would they find the same solution? So to get an intuition into that, we will take a very simple example. So this is the AB example. So it's just an MDP with 2 states, A and B, and each row is a different episode of experience that we've seen. So in the first episode, you start in state A, you get a reward of 0. Then you go to transition to state B, and you get a reward of 0, and then the episode terminates. The next episode, you start in B, you get a reward of 1. Next episode you start in B, you get a reward of 1. Scroll down here, you see an episode you start in B and you get a reward of 0. So the question is for you guys, what's the value function? So any suggestions? What's the value of A and B? So let's do the easy one first of all. What's the value of B? So we've got 6/8. Right, so we've got 8 episodes starting from B. 6 of them got a value of 1. 2 of them got a value of 0, so I think everyone would agree the value is 6/8 or 0.75. What about the value function from A? Any volunteers? Okay, we've got one person says 6/8. Any other
Zero.
guesses? 0? Okay, so who thinks 0 and who thinks 6/8? Let's have a show of hands for 0. Okay, who thinks 0.75, 6/8? Okay, good. About, of the people who said, about half and half. So those are respectively the Monte Carlo and the TD solutions to this problem. They're both perfectly legitimate solutions, and we'll see why. So first of all, the 0 answer, I think, is the 0 one's easy to explain. We've seen one episode from A, and we got 0 reward on that episode. The return was 0 from this point onwards. So the value function, legitimately, we could estimate as 0 from that point onwards. Okay, that's the Monte Carlo estimate. We looked at complete trajectory starting from A. We had one complete trajectory starting from A, it got 0. What about the TD estimate? Well, implicitly, what this is doing is something like the following, which is it's building implicitly. Imagine that you were trying to build an MDP model that models what we've seen so far. Okay, if you were to build an MDP to try and explain this data that you've seen so far, you would build an MDP model that looks like this, where you start in A, and 100% of the transitions that we've seen where we started in A transition to B, and got 0 reward along the way. And once we got to B, 75% of the transitions gave us a reward of 1, and 25% of the transitions gave us a reward of 0, and then we terminated. So that MDP is the best explanation. So this is the maximum likelihood MDP that explains this data in the best possible way. Okay? So now we understand that, we can see what these guys converge to. So Monte Carlo always converges to the solution that minimizes the mean squared error. So it finds the best fit to the actual returns that we've seen. So if we saw these particular returns, Monte Carlo just minimizes the mean squared error over all time steps, all episodes. It minimizes the difference between the return that we saw and the value function, which will be capital G. Whereas TD0 actually converges to the solution of the MDP that best explains the data. So implicitly what TD is doing is it first fits an MDP, and then it solves for that MDP. So whatever data you've seen so far, it will find the solution to the maximum likelihood MDP model that explains that data. So this is just math to say exactly that same idea. It's just saying that, first of all, let's find the MDP that best fits the data, and you can do that just by counting transitions. So here this is just saying let's make the transition dynamics count all the transitions we've seen from state S and state A to some other state. Let's count those transitions and make that the probability. Just count the transitions and divide by the total number of times we're in S and A. And the reward is just the mean reward from state S and A divided by the number of times we were there. It's just fancy notation. This bold one means an indicator function, saying each time this event occurred, this indicator has value of 1, otherwise it has value of 0. Yeah?
If you know the MDP, can you give it to Monte Carlo so that it doesn't, do you know what I mean? So
Right, so the question is, if you know the MDP, can you give it to Monte Carlo to ask it to sample from the MDP and work from those observed returns? We'll come back to that in lecture 8 or 9. We'll do exactly that. It's a good idea. Okay, so let's come back. We were trying to understand the advantages and disadvantages of Monte Carlo and TD. And so I really just want to summarize the third type of advantage now I think we can understand better, which is that a Markov decision process has the Markov property. And TD exploits this Markov property, exploits it by building implicitly this MDP structure and solving for that MDP structure. And that means that in Markov environments, TD normally is more efficient because it actually makes use of that Markov property. It makes use of the property that you don't need to just blindly look at complete trajectories. You can understand the environment in terms of states, and we know that certain properties of those states have to hold, that the state has to summarize everything which came before. And that's why TD is more efficient. It's another way to understand it. Whereas Monte Carlo does not exploit the Markov property. It ignores the Markov property, but one benefit then is if you're in a non-Markov environment, partially observed, you can't just rely on the state signal, you get everything's aliased and messy, then Monte Carlo can be a better choice. And often we have some spectrum between these where you're maybe a little bit non-Markov, and then the question is, how far between these should you go? Okay. Right. So just to sort of summarize where we're up to, this is just a few slides to give a sort of pictorial summary of what's going on. Yeah, question?
You said sometimes we're a little bit non-Markov. Does that mean an MDP even still applies?
Okay, let me explain that comment. So I said you can be in a situation where you're a little bit non-Markov. So the question is, does an MDP still apply? So under the hood, there can always be an MDP which defines the way that the environment works. And the question is, what do you observe as an agent? So a partially observed Markov decision process is where you get to observe some function of the state. You get to see some part of the state. You get to see like certain cards but not other cards, or you get to see certain statistics but not other statistics. So there's an MDP running under the hood. You get to see some part of it, and now the question is, how do you deal with that? So there is an MDP, yes, but if you just try to use your observed statistics as your state representation, TD wouldn't work very well. TD0 wouldn't work very well. Monte Carlo would still do the right thing given that representation you've given it. So it would still find the expected return conditioned on the information that you've shown it, which might not be great, because if you have a blind robot walking around, its estimates of the value aren't going to be very good compared to if you let it see everything. But you still want to make sure that it can consistently estimate values, even if it is blind, even if you only give it partial information. Okay, so let's just try and pull things together a little bit. So we've seen that we have these different updates which take these particular forms, and we can think of these as like backups. That we started in some state. Imagine we're doing something like our backup diagrams we saw for dynamic programming now, where what we're going to look at is you start in some state, and implicitly there's some kind of look-ahead tree. Like, we're in the MDP, and in this MDP, from this state, there are two actions I could take. I could go take this action or this action, and from those actions, the wind might blow me here or it might blow me here. Then there's some actions I could take. This one might terminate. This one might, the environment might take me to here, and so forth. And the question is, how do we make use of this look-ahead tree to figure out the value function at this root node here? And so what Monte Carlo does is it basically samples one complete trajectory along here. It samples it samples an action from the agent, it samples where the wind might take you, it samples an action, samples where the wind might take you, samples one consistent trajectory. Just by running that and interacting with the environment, you get one sample of this whole thing. And then you use that sample to update the value function at this root value here. And we also do it at every intermediate value. This is just showing what happens for one. We're focusing on one state here, but we also do all these other updates when we run. Temporal difference learning, the backup, is just over one step, where we sample the environment, we sample our own action, we sample the environment, we look at the value function where we ended up here, and now we back up that value function here towards the value function at this root node here. So we don't go all the way to the end like we did in Monte Carlo. We just look one step ahead. We get a sample of what happens over that one step. We back up that sample towards the value function here. Now let's contrast that to what we did in dynamic programming. So in dynamic programming, we also did a one-step look ahead, but we didn't sample. We had to know the dynamics, and we used those dynamics to basically compute a full expectation. Well, now we consider this action here. We took a full expectation where we had to know the probability the environment would take us here. We had to know the probability the environment would take us here. And then we could sum these values together, weighted by their probabilities, take a max over our actions, and do a complete backup to figure out the value here. So if you know the dynamics, you can do this full look ahead, and that backs you up completely to give you this value here. And just to complete the space of possibilities, you could also do an exhaustive look ahead of this entire tree. You could do something which is like dynamic programming, but you went all the way to the end and did a complete backup, and that's an exhaustive tree search. So you get an exponential blow up in the size of the update that you do for just one state. So let's try and tease these apart into dimensions that we can understand that sort of define our algorithm space. So the first dimension is whether or not we bootstrap. So Monte Carlo does not bootstrap. So bootstrapping, again, remember, is this idea that you don't actually use the sample, you don't actually use the real returns, you use your own estimate of the returns, you use your own value function as a target, and you use your estimated value function to kind of give you an iterative update, rather than using real returns or real rewards. So Monte Carlo does not bootstrap, it uses the real returns all the way. But TD and dynamic programming both bootstrap. So in both TD and dynamic programming, we were doing something like the Bellman equation, where we look at the immediate reward you get plus the value function at the next step, and we bootstrapped from our estimated value at the next step. So in both of those cases, had that situation. You've got your robot, you take one step of real experience, but then you make a guess of how much value you're going to get from here until the wall, and use that guess of your value to back you back up, either from one sample in TD or by doing an exhaustive full width backup in dynamic programming. The other dimension is whether we sample or take full width backups. So Monte Carlo samples, so it samples the environment. We don't need to do a full width exhaustive search over all the things the environment might do. We sample the MDP dynamics. We sample our own policy. Whereas dynamic programming does full width updates. It considers every possibility exhaustively and backs them up exhaustively. TD samples as well. Okay, are these two dimensions clear? Good. So that gives us this picture, sort of gives us the space of unified view, if you like, of methods for policy evaluation. We'll also have the same picture for control that applies throughout reinforcement learning, where you can either use these full width backups that do this exhaustive look ahead over all the different choices you might make, or we could sample the dynamics. And then in this dimension here, we've basically got methods which bootstrap from our value function after one step. So they only have to go like this shallow look ahead. They look ahead one step and then update from the value function here towards the value function here. Or in dynamic programming, we do a full width look ahead, but we update from the value function here to the value function here. In contrast, we can do these deep backups with Monte Carlo, where we go all the way to the end of the episode and we look at what happened right at the end, and we back up the actual return all the way to the value function here. Similarly with exhaustive search, you can do an exhaustive look ahead all the way to the end, back that up all the way to the root, without ever bootstrapping from your own value estimate. Okay, and now the final piece, in the remaining 20 minutes or so, I'd like to talk about a spectrum of methods in between these shallow and deep backups. So it's not actually the case that you have to do either or. You don't have to do either TD learning or Monte Carlo learning, because it turns out that there's a unifying algorithm which has either end as its special case. And that algorithm is called TD lambda. We'll see that lambda basically lets you pick your place along here, where you can be either shallower or deeper according to a value of lambda. Yeah, question?
So I have one question about the TD learning algorithm. So whenever we sample state action transition to another state, we always update the value function for the first state of the action. So it's sort of saying I'm updating my estimate of the state where I was given the current action, and I assume that actually the next value is correct. Why can't, if we do the opposite way, so we update the value function for the forward state,
Okay.
we basically do the opposite.
All right. So
In that kind of scheme, would it be true that it should also work?
yeah. So it's a great question, which is why do we assume that the value after one step is more accurate than the value before one step? Why not? Why not reverse the dynamics and do it the other way? And the second part of the question was, would the alternative algorithm give the right answer? So the answer is that it would give the wrong answer. In fact, even if you do something like just make these things close to each other and try to minimize the mean squared error of your TD error or something, you find the wrong answer in stochastic MDPs. That's a well-known fact. You actually get the wrong answer by doing it the other way. So why? So let's get the intuition. So the intuition is that if you take one step, you're always, in a sense, a little bit more accurate because you've seen one step of reality in between. So you've seen one step of reality. That step of reality involved one step of the real reward and also one step of the real dynamics. And then you estimate your value function where you ended up. Okay? But because you've included one step of the real dynamics and the real reward, you are, in some sense, more accurate. You're more accurate than where you were before. And if you take enough of these steps, you end up grounding yourself completely in the real dynamics and the real reward of what happened. So it's because you're involving one step of the real world. Whereas if you go backwards, it's like you're starting from a situation where you've already taken that step, you're closer to your goal, you've already seen this real step of what happened, and now you want to use this guy to, you're going to move this guy towards your estimate of what happened before you saw that real step of the environment. there's no reason to think that that estimate is actually going to be better, and often it's going to be worse. So I think the key is, and this is actually comes apparent in the math if you actually look at the reasons these algorithms converge, like contraction mappings and so forth, is because you take one step of real dynamics, and that real dynamics always brings you closer to the ground truth.
Yeah, but if you make the step backwards, you still observe the real dynamics of the reward that you get. Should that get you closer? And I'm not
No, I
sure
don't think you do in
also
reverse.
For given MDP, does there exist another MDP which can produce the observations in reverse order? I would guess not, if this one doesn't exist.
So if I have time in future lectures, what I'll try to do is give a specific MDP for which your proposal fails. And it's very simple. There's a very simple MDP, and we can maybe do it afterwards. Okay, but I really want to do TD lambda before we run out of time. But yeah, great question. Okay, so far we've seen this idea of temporal difference learning, where we said, okay, you can take one step of reality and then look at the value function after one step. But why not take 2 steps of reality, where you take 2 steps and then you look at the value function where you ended up and use that value function after 2 steps to back up towards your value function of where you were 2 steps previous, or 3 steps, or n steps. All of these are valid ideas. They're all reasonable. And so what we're going to do is generalize the idea of TD learning to these n-step predictions. So TD we can think of as this special case. TD0, what we've seen so far, is a special case where we take one action, so we see one step of the environment, we end up in some successor state, and we update the value function of that successor state towards our value function at our original state. But we could just as well do the 2-step version, where we take one step to our next state, another step to our state 2 time steps from now. We update the value function, our reward plus our value function gives us our estimated return, and we update our value here towards that estimated return. So you can do that for any number of steps. You can always say, well, I'm just going to observe some number of steps of the real world, see how much reward I got along those steps, add on my estimated value from that point onwards, and that quantity is a valid estimate of the overall value function. And we can use that estimate to update our original value function in the correct direction, based on the comments to the last question. Okay, so let's specifically try and just write out what that means. So far we looked at the TD0 estimator. That's when n equals 1. So when n equals 1, we make what we call a 1-step return. This G1 is a 1-step return, where we just look at one step of the real return, and we look at our value function in the state that we ended up in after one step. But now let's define the 2-step return. So the 2-step return, this G2, is the reward after one step, plus the discounted reward after 2 steps, plus the twice discounted estimated return from that point onwards. So this is our value function. Our value function tells us, from that point onwards, how much reward are we going to get? And then we can just say our overall return, our estimate of the overall return is our real reward after 2 steps, plus our estimate of what's going to happen from that point onwards. So we can do this for any n, and in the case where n goes to infinity, we end up with the Monte Carlo estimator, the real return. So we start off with TD0 here, and we get all the way to Monte Carlo here. The reason we get to Monte Carlo is because G infinity, we use all the steps of the real environment. We look at our real reward plus our discounted real reward at the next step, all the way until the end of the episode. We're just looking at the real rewards of what actually happened in that trajectory, and that's exactly what Monte Carlo does. It looks at these real quantities and it uses those as our targets. And so now we can define, if we just generalize this for any n, so the n-step return just tells us we're going to take n steps of real reward by really interacting with the environment. So these are just random quantities that depend on our particular trajectory of where we ended up over n steps. And then after n steps, we can use our estimated value, our current value function, in the state that we end up in after n steps, as like a proxy for all of the rewards that we haven't observed from that point onwards. And we use that as our estimator. And we can plug this in the same way that previously we took our Monte Carlo estimate and we plugged in our TD0, our TD target, in place of the actual return. Now we're going to plug in our n-step return as our target. So what's this telling us now? Again, we've got like this error term here, where we're saying we started off with some estimate of the value function. We ended up, after this particular trajectory, with some n-step estimate of that value, where we saw some number of rewards and plus our estimated value. So this is our n-step estimate of the reward. This is what we thought the reward was going to be. That generates an error signal, and we just update our value function a little bit in the direction of that error signal to correct for that error. So this is valid for any n. So which n is the best? That's the natural question. Should we be using n equals 0, which was TD 0? Should we be using n equals infinity? Should we be using n equals 17? What's the right thing to do? So this is a little study just on the same random walk we saw before, but now this is a larger case. I think it's got 21 states or something like that. And it's just a little study to look at how the performance, in terms of this root mean squared error that we looked at before, how it varies across different step sizes that we varied before, but also across different choices of n. So these little numbers in here tell us the choice of n when we do n-step TD updates. And the top and the bottom diagrams are very similar. It's just about whether we do online or offline updates, and that means whether we immediately update our value function or whether we defer the updates of our value function until the end of the episode. And you get slightly different results, but the character is still the same, which is to say that as n approaches infinity, up here somewhere, you see what would happen if you were using Monte Carlo learning. So you get very high errors. I think all of this is, these are short runs. With this, the total training time is short, which is why Monte Carlo, the difference between them is so exaggerated here. But we see that Monte Carlo, the variance of Monte Carlo is high, and it doesn't do very well. TD exploits the Markov property, it's lower variance. It does better. So this is TD 0. But in between, you get this sweet spot where if you look ahead just sort of the right number of steps in your trajectories, you can propagate information backwards more efficiently. You can kind of, each TD update is not just propagating information back over one step, it can propagate information over multiple steps, over n steps at a time. So you can kind of move information more quickly across a long chain now by using n greater than 1. And so we see there's some kind of sweet spot with n around 3 or 5, but it's sort of unsatisfactory in that you can see that even between the online and the offline, the best n changes, and if you change the size of your random walk, the optimal n changes again. Like if you were to do a 100 state random walk, you would see that all of these values would be shifted over so that you should have to favour larger n. And so it's a little bit unsatisfactory. We want to have algorithms which are sort of robust across many different ways to many different n's. And so what we're going to do is try and come up with an algorithm which gets the best of all n. That's the goal, to efficiently consider all n at once. So how do we do that? Well, the way to do that is to notice that we can average over these n-step returns. We don't have to just commit to one of them. We can actually take a target which combines multiple n-step returns together. So for example, consider this case where we're just going to do one backup towards the average of both of these. So basically what we're going to say is our estimate of the return now is going to be what happened after 2 steps and the value function. So we're going to take 2 steps of real reward and the value function after 2 steps. We're going to average that with 4 steps of real reward and the value function after 4 steps. We can average those things together, call that the target, and that thing is going to be more robust because it kind of gets the best of both of these cases. And we can use that as the target for our TD learning. And so the question is, how can we efficiently combine all n in this way? Can we come up with a scheme that, without increasing the algorithmic complexity, lets us deal with all n? And the answer is, yes, we can do that efficiently. And the algorithm basically is called TD lambda that does that. So the main idea is to use this quantity which is called the lambda return. And the lambda return is like a geometrically weighted average of all n going into the future. And so the idea is that we've just got this constant lambda, which is between 0 and 1. And this constant lambda tells us how much we're going to decay the amount that the weighting that we have for each successive n. So we're basically going to have a weighting of 1 minus lambda for this one-step look ahead. And then we're going to keep multiplying successively by lambda. So this 1 minus lambda is just like a normalizing factor that makes all of our weights sum to 1. So what we're going to do is multiply our weight by lambda when we go to from n equals 2 to n equals 3, by lambda again when we go to n equals 4, and so forth. So each one is successively weighted less and less and less until we get to the end of the episode, and we basically give all the remaining weight. If we were to continue this diagram all the way to infinity, we're going to sum the weights of all the remaining ones, gather those weights together, and put them into this final update for the last one. Okay? So this is what it looks like. So we use a weight. For every n-step return, we weight that n-step return according to 1 minus lambda, this normalizing factor, and then just lambda to the n minus 1 times n. And so this is our lambda return. This g superscript lambda tells us our weighted sum of all of our different n-step returns. So we're going to weight these together geometrically. And now again, we're going to do the same trick, which is we're just going to use this g lambda as our target now for TD learning. We're basically going to move, we're going to have our estimate v. We're going to use this thing as the target, our weighted sum of all of these n-step returns. And we're going to generate an error. This is what we thought the value was going to be. This is after our trajectory, after a whole episode, we can weight all of our n-step returns, come up with this very robust estimate of what the return actually ended up looking like. And we update our value function a little bit in the direction of that error signal. Is that clear? Maybe. Yeah, question.
Is it always the case that the last weight in this formula is smaller in comparison to the previous?
It's always the case until the final step, until the algorithm terminates, that the weights are getting less by a factor of lambda. The final weight actually can be larger. Just think of this as you can always take any episode that terminates and replace your terminating MDP by an MDP that goes on forever, and it just stays in the same state, getting 0 rewards again and again and again. And so all this is doing is instead of, so you could have a diagram which goes on forever, where these were getting longer and longer and longer, and the value function wouldn't be changing each time because you'd just be stuck in that same terminal state. And then all this is doing is gathering together all of those final ones into one update because we know that the episode's terminated. So it's just an efficiency that we gain by knowing that the terminal signal has this special effect that nothing else is ever going to change the value after that point. But it can be larger. Okay, so it looks something like this, where we've got this weighting, and this weighting decays geometrically like this over the number of steps that we look into the future, and we generate this lambda return, and we kind of sum up all of the final steps into one bigger weight that we use to deal with the final return, the last step of the episode. You have a question?
Why is it geometric weighting, right? Why don't we use some other convergence?
Okay, great question. So the question is, why use geometric weighting? Why not some other weighting? The answer is that it makes for an efficiently computable algorithm. So the geometric weightings are memoryless, and that means that you can actually do this in a very efficient way that doesn't require either storing or computing something different for each of your n-step returns. So you can do TD lambda for the same cost as TD0, basically, same computational cost. And that's only true for geometric weightings. You can, I should say that it is possible to come up with geometric weightings where the lambda varies per time step, and that gives you a much broader class. And that still has the nice property. You can vary the lambda that you multiply by at every step of the algorithm. That gives you a much broader class, but it still satisfies this nice property. So we are going to make use of that property shortly as well. Okay, so what we've seen so far is that we have what we call this forward view algorithm, where it was a bit like Monte Carlo, that to do this we had to wait all the way until the end of the episode to get our n-step returns. But you can only compute what happened after 10 steps from now. Once your whole episode is finished, you can go back and look at all your n-step returns, average them together, get your lambda return, plug that into your algorithm. So this suffers from some of the same disadvantages that we had with Monte Carlo. So that's the forward view of TD lambda. But what's nice about TD lambda is there is an equivalent mechanistic view that achieves the same results as forward view TD lambda, but without having to look into the future, without having to wait until the end of the episode and gathering those lambda returns. So this is just to say this is the same diagram we had before, showing on the large random walk, now how sensitive is this to lambda value? And it's actually, we see that there's a sweet spot again in lambda, but it's actually much more robust, that this value of lambda would be the same, that works best regardless of the size of the random walk. It's much more robust to the change in the environment, and it does well, as well as the best n, just by averaging over these things. And lambda equals 1 is Monte Carlo, lambda equals 0 is TD0. And we see that we can do much better. And you often see these kind of curves where there's a sweet spot in the lambda curve between 0 and 1, where you get just the right trade-off between bootstrapping and the bias variance trade-off. Okay, so now let's come up with a backward view. How can we actually achieve this, but with the nice properties of TD learning, where we update online every step from incomplete sequences? And that is the TD lambda algorithm. So to understand that, I'm just going to put up one diagram here. Okay, so imagine you thought you're a rat again, like in the first lecture, and you thought you were going to get this nice piece of cheese, but then you hear a bell 3 times, a light comes on, and you get electrocuted. Okay, so who thinks that you got electrocuted because of the bell, and who thinks you got electrocuted because of the light? Let's just have a show of hands. Bell. Light. Okay, so most people thought the light. Okay, they're both reasonable answers. If you thought that the most frequently occurring state caused this event, then you would assign credit to your error to the bell. You would say the bell happened more, so that was probably the, I thought that I should change my thinking more because of the bell than I should because of the light. But there's also a recency heuristic, which apparently you guys are partial to, which is to say the most recent thing which happens should basically be assigned credit for the error that we see. And the idea of eligibility traces is to combine both these heuristics together. So what we do with eligibility traces is we look over time at the states that we visit. And so this is the eligibility trace for one particular state. And this is the moments at which we visit that state. And what we do is we basically, every time we visit that state, we increase the eligibility trace. And as we start to not visit it, we decrease the eligibility trace exponentially. So we increase it, we see it, we increase it again, we increase it again, and we don't see it for a long time, and it sort of decays off. And so this gives us our frequency and recency heuristics combined together. And what we do is we basically when we see an error, we update the value function now in proportion to the eligibility trace, in proportion to how much credit we think was assigned to being in that state. Like how much was being in this state of hearing a bell the cause of this error that I saw, and we update the value function there directly in proportion to the eligibility trace. So this gives us the backward view TD lambda algorithm. And so what this gives us is this following algorithm, where for every state we're going to keep one of these eligibility traces. That's trivial computationally, it's just a simple operation per state. We update the value function for every state in proportion to both the TD error and the eligibility trace. So we compute our TD error. This is what we thought the value function was going to be. This is our estimate of the value function after just one step. So this is the one-step TD error. And now we basically update our value function in the direction of the TD error in according to our credit assignment. So we basically see this error, and the things which have the most eligibility, which we think are most responsible for that error, get updated the most. And so this has this like backwards view now, where we're no longer looking into the future. It's more like this TD error is being broadcast back to every state in the past, and the value function at each of those states is updated in proportion to the TD error. So how does this relate to the algorithms we've seen so far? Well, trivially, we can see so far that when lambda is 0, that this reduces to the TD0 algorithm. So if we plug in the eligibility trace for lambda equals 0, we see that the eligibility trace will be, when lambda is 0, basically what that means, so lambda is telling us how rapidly we decay this thing. If lambda is 0, we declare it completely, straight down after we've seen a state. So that basically means we only assign eligibility at the state where at the moment that state is visited. And so we basically update our value function in proportion to this thing, which only will be updated if we actually visit that state. And that's exactly what TD0 does. It basically gives us our update. And for the state that we visited, we update the value function in proportion to the TD error for that state, only if that state was visited and never otherwise. Okay? at the other extreme, we have lambda equals 1, and in that case, the credit is deferred all the way to the end of the episode. And so if we're actually in an episodic environment, this has the nice result that actually if you were to accumulate all of the updates that you do using this backward view, you actually end up getting the same set of updates. The sum of those updates is the same as for the forward view of TD lambda. So the backward view and the forward view of TD lambda are actually exactly equivalent when you do offline updates. They're the same algorithm. So it's just a mechanistic view that can be implemented efficiently. You only have to look backwards, you don't have to look forwards in time. And that's the TD lambda algorithm, which helps you achieve this principled view, which we understood in terms of this forward view, where we were doing these averaging over these n-step returns. So this theorem shows that they're equivalent. There's some notes which you can look at offline that prove the equivalence and give a bit of intuition into it. And finally, there's just a mention of some recent work that shows that actually this result has been extended even to online updating as well. So even if you change your value function as you go along, you can also achieve the same equivalence using a recent method from last year. So that's it really. So that's all in the slides. So just before we close, any last questions about that? So TD lambda basically gives you a spectrum. It gives you a spectrum between TD0 and Monte Carlo. And it has two implementations, this forward view that gives you this theoretical way of averaging over all your n-step returns, and this backward view where you accumulate these eligibility traces, and the eligibility traces can be very efficiently updated and just tell you how much credit you should assign to each one of those states. So you never need to look into the future, and you have all the benefits of TD in terms of working from partial sequences and so forth. But you can pick your point now just by choosing lambda. You can pick, just like in this plot, you can pick your lambda so as to get the benefits of both, to get a sweet spot in between Monte Carlo and TD updates. Okay, right. Assignment will come online shortly. We should probably get out of here to let the next guy in. See you after reading week.